Hi, hello everyone. Thanks for being here. I'm Gabriel. I was a Canadian, and for the last couple of years, we've been building GeoServer Cloud, which is basically GeoServer, GeoServer components, but decomposed functionally into several microservices and provide a security solution based on with Docker compose or with Docker compose and controls. So, GeoServer Cloud, since GeoServer is based on Spring, it's a natural evolution to adopt a Spring Boot in order to have independent standard applications that can be deployed and be provided in Docker images, and the Spring Cloud to provide service discovery and load balancing, metrics and culture, standardized application configuration, and distributed events. So the agenda for today, I don't know how many of you are familiarized with GeoServer itself. You are. Okay. Have any of you had been in contact with GeoServer Cloud already? Then we will go through the requirements that we have to create a solution. More importantly, to find what challenges, what technical challenges we need to face in order to comply with those requirements and describe the outcomes. Finally, I will answer some questions to the capacity or whatever approaches. So, problem statement. GeoServer is used in enterprise environments not only as a front-end service to publish data, but as a backend service to support business process. In that capacity, it's very common to have certain level of scalability requirements that go beyond what you will find in the front-end application or in front-end deployment. Including, people go crazy and have hundreds of thousands of layers on workspaces, services by workspace, and not that kind of stuff. On the other hand, current enterprises or companies have their own cloud native or cloud-based solutions for infrastructure that they need to deploy to server on. So we need a solution that works well in those environments, that can scale up and down, in and out. Sometimes for the sake of, for technical reasons like high availability, throughput on the road, and other times because there are budget constraints if you're deploying on a cloud-native provider, you may be paying costs for over mentioning your vanilla GeoServer clusters. You rather have the ability to stay down when there are not so much demand, stay down when it's required. So historically, it has been rather cumbersome to set up such kind of clusters with vanilla GeoServer current historical deployment options go from having several instances of GeoServer in fixed machines with a fixed number of instances, having to set up master, slave, cluster setups, having problems, especially having problems with keeping the configuration of layers, data stores, services, etc. In sync across all instances, or even being forced to reload, restart or reload the configuration. That used to be mostly a problem when you have a large data directory. You have 10,000 layers, you have 10,000 small text and modifiers only from layers, but you have to multiply that for 4 or 5 for the data stores, for the workspaces, for the layer feature type, and so on. So, we wanted to provide this version of GeoServer that could work in this environment, that could be versatile enough, that could handle a large number of configuration objects. And starting with the requirements to do that, there are not that much. I mean, GeoServer is already great and it's modular, but we need something that scales, that can scale capabilities independently. Like for example, in my company, we need a large number of WMS instances. Maybe I'm okay with one WFS or occasional queries. I don't need the WPS. The REST API has to be there. It only has to be available to my internal network. I'm not that kind of stuff. Speaking of the backend configuration, it would be better if all these instances that I want to launch indefinitely could share a data directory instead of having to have their own copy with the risk of they become out of sync. So, what do we do with that? First thing is to think about architecture. So, in this ecosystem, we have Spring Cloud. Spring Cloud is a framework, a number of libraries, and extensible ready-to-use application servers to create cloud-native applications or microservices-based applications that solve the most common patterns for this kind of applications. For example, Verizon API Gateway, which is a proxy to backend services that provides a service registry where you can spin up and kill pods, and maybe Kubernetes decides to build some pods, maybe you need to scale down. The services will register to this service registry, and it will allow all the other ones to, whenever they need to communicate with other services, to perform automatic load balancing. It also provides configuration service, so your applications can rely on externalized configuration. So you have your Docker images, you launch your containers, so you don't need to be fiddling with the containers file system to add externalized configuration. It will just get the application-specific configuration from the configuration server. And the configuration server at the same time could be loading the configuration from files in the file system, from a Kubernetes config map, from a Git repository that's remote, or GitHub, or whatever. So, speaking of architecture to the rescue, GeoServer Cloud's architecture protocol. It's composed of also the discovery, the config that's provided by Spring Cloud. And then we need to separate GeoServer specific capabilities into their own microservices. And we will see how to do that in the future. Another thing I forgot to mention is the devOps. That's also is an abstraction provider, Spring Cloud also, that lets you work with distributed events that span across the cluster nodes. Being an abstraction layer, it sits on top of Spring Cloud stream, which is where it actually will bind to a message broker, whether it's RabbitMQ, Kafka, Amazon, whatever it's good, and so on. So far so good. It looks very good, and that's how we started the project. We're excited about it, but there is some details, and that is what I'm going to talk about that, those details, the little doubts or technical issues that we found and how we solved them for GeoServer Cloud to be a reality. So, first requirement was that these services we need to split GeoServer monolith, which is a huge application with an immense number of components and plugins. We needed to separate them into pieces that make sense as standalone services. So what are the challenges here? Basically, we need to perform some sort of functional composition by capability. We wonder how the micro is in microservice in this context. What do we draw the line? In the case of GeoServer, it makes sense to wrap each OGC service and make it its own standalone independent service or microservice, where you could maybe dimension the containers based on the specific requirements of that service. For example, WMS will need more memory because it needs to create enough images in memory. And maybe not so much processing power, maybe it will, but it's probably the one that we need the most. WFS, it's streaming. It's writing data from the backend and spinning out to the response. It doesn't need so much, so you want to dimension them appropriately. So in this, to do that, GeoServer modularity really paves the way. Yet there are interdependencies between components that we need to deal with. For example, if you had the GeoWeb cache service as a separate service, it still needs the rendering engine from WMS to create the target images when they are missing. At the same time, sorry for the story, but I can cut it. For example, in the WMS, at the same time, you need the GWC, the GeoWeb caching engine. If you want to integrate the WMS caching protocol to the WMS. But in the WMS service, you don't want to expose the GWC services. In the GWC service, microservice, you don't want to expose the WMS service interface. The capabilities is not on that. That's not free. So the problem with that is that GeoServer, being Spring-based, loads everything that's in the class path. It defines which components, which beans to define the core planning, the core system in an application context XML file. The Spring will load everything that's in there, and hence you cannot cherry pick which components are going to be on each specific microservice. And we rather avoid like having all the services calls on the microservices, because that is exactly what we are trying to do. So how we solve that? By one side, with careful dependency management. We are using a lot of major exclusions to avoid having transitive dependencies that are not needed on each specific service. I'm going to go fast about this because maybe it's too much detail. So, for example, you see in GeoServer you can configure metadata for the WMS service, for the WFS, for the WCS, etc. That's performed through configuration classes that are specific to those services and are on those components jar files. But depending on that jar file, carries over a lot of transitive dependencies that we don't need. So for example, if in WFS, I will need to have a dependency on the WMS jar just to be able to cope with the configuration. We make a configuration change. I need to be able I need to have that configuration class available, or the dialog will crash, but I don't need all the dependencies. So in order to solve that, we created a custom XML bean definition reader, where you can use where we use regular expressions to lead from which jar files in the class file we are going to load expressions, and to create either whitelists or blacklists of which beans in those XML files to load. The other option would be to translate the whole set of bean definitions in the XML files to Java configuration files, but that's cumbersome. That's repeating a lot of stuff. We rather use what we can from the XML files, check which beans are going to be loaded for in each service, and override the Java configuration files only what's necessary. And the other part of this solution is to use Spring Boot other configurations. So how it works with GeoServer, if you want to install an extension or let's say a plugin, you drop some jar files in the webbean/lib directory, and just let it load everything that it finds in there. Since we are providing pre-configured or pre-cooked Docker images with the extensions that are already adapted to GeoServer Cloud, you still need to be able to decide as a DevOps, or for example, which components, which extensions are you going to load, or use externalized configuration to set some configuration settings. So other configurations are the means provided by Spring Boot to create plugins. Plugins that you can use declarative conditionals to define whether they are being loaded to the application context or not. So the next requirement is that it has to be ready to handle huge parallels. So what challenges we find here, essentially we have problems related to the data directory. Let's call it the data directory implementation of the parallel configuration backend. And we have problems to have alternative parallel configuration backends implementations. So the data directory you have memory footprint. Let's say you have this system, all the microservices, you're starting a new system, all the microservices are starting at the same time. Right? If you have the Canada with those 20, 50,000 layers loaded on each node in memory, that's a little bit of reasons because you need a proportional amount of memory in each node, and you may be launching a node 20 LMSs or whatever. On the other side, another problem with the data directory is that loading that many thousand small XML files from the file system can take ages. Especially when you are when you are using a shared data directory, that of course will need some sort of shared drive, like an NFS mount or something like that. And over NFS, it is particularly slow to do so many I/O requests for small files. If it's one large, very large file, it's okay, but loading thousands and thousands of small XML files, that's forever. If you don't want to go that way, you could use, okay, I could use an alternative catalog backend. Currently, the only alternative implementation in GeoServer Cloud base is a JDBC config that allows you to store the catalog in a relational database. But it has its own pitfalls. Like it suffers from multiple requests for each point where if you want to fetch one layer definition, it's going to make separate requests to get the layer's resource definition, like the feature data, a separate query to get the workspace, the namespace, and the store. So, and when you do range storage, the other layers or the boundary layers, that you got to multiply that for the number of layers you're fetching. So we can go, okay, JDBC config contract, data store backend is slow for large catalogs. I want to implement a separate one. And I want to go crazy and do MongoDB. Or a better implementation on a relation in a database whatever. Problem is that it is quite difficult to do that because of some design problems with the catalog interface on the default catalog implementation and the default catalog it's called catalog facade. It's actually a data access option, what's supposed to be. So there is no clear separation of concerns between those two. It makes it difficult to implement an alternative backend where I should only focus on dealing with my backend, like fetching the data from the database and sending it to the database, and instead I have to deal with the catalog events with the modification process, which is totally, let's say, an implementation detail for the catalog, not for the catalog facade, in my opinion. So, how could we solve this? Memory footprint and unknowns, there is not much to do. Loading a certain number of objects in memory takes or takes. For reading so many thousands of small files, okay, we can try to do better. So we implemented an optimized data directory loader that what it does. Oh, great! So easy to is to load all the system files in parallel and try to do one single pass over all the directory structure, which is much bearable for an NFS drive, for example, instead of doing random access, like Grace. Well, we can, for HPC config, we could use Wiki Bouncer to limit the connection observation problem. For resolutions, when you start multiple services at the same time, and you find that the JD's config backend is trying to create configuration properties in the database all at the same time, okay, we fix that with some distributed lock mechanism to make sure that only one instance will rather lock, create whatever is necessary in the database to function, and then release the lock, and the other will say, okay, the metadata is already in the database, and I need to recreate instead of all of them trying to do it at the same time. For implementing additional packages, we created new kind of plugins that covers the application level of responsibility of dealing with the notification process and the events and an extended parallel facade, where you only have to implement it in order to deal with your actual data, with your raw data, and convert it to info data, info, etc., and let the parallel that's calling you deal with the rest of the stuff. Now, as part of the shared data directory, which is the next requirement, there are ways and issues in GeoServer. If you try to start several instances of the same data directory, it will crash. So we basically created or introduced distributed logs on critical sections that try to update the stuff on the directory when they set up. Same thing, distributed log. The other problem in doing that, we find out that the file-based distributed logging in GeoServer is flawed. It's implemented in a way that if you want to log a given resource, you give it a name, it will create one small file, log that file, and do whatever it has to do, and then run it. The problem with that is that if two separate processes are trying to log the same file, they open a file channel, and then one of them wins the log on the file, the other is waiting, but the one that won the log then deletes the file, and the other one still has the file channel open, because file channels will stay open until all of them are closed, independently of the file name existing now. So you solve that with an internally distributed file of implementation that is responsible to log anything. There are other resolutions that were also fixed with log logs. Okay. To finalize the final requirement was to maintain the parallel and sync. So we are using distributed events. Whenever an instance makes a change in configuration object, the distributed event is sent to all the instances, and instead of sending the warlock, it's sending a batch. And with that batch, we are not competing for core object overrides in all the instances that get notified. Fixed redundancy and lack of distributed nature of the resources provider. we can skip. And so through that, we got to deal with all these pitfalls to finally get GeoServer Cloud up and running and in production. GeoServer has 800 K lines of code, and GeoServer Cloud has another 50K on top of that. We're in version 1.2 currently to 45 releases to that. It's already in production in several African customers. You already have come to come, it's a great company, and we need to move on. Thanks for your attention.